Hi to those watching this video, I'm Tian. Today, we're presenting our project on the fault injection testbed for autonomous driving agents using Carla. This work was conducted by our team consisting of me, Tian, Kyle, and Kelly. As we move into an era where software is taking the wheel, the reliability of that software becomes a matter of life and death. Our project focuses on stressing these systems to see not just if they can drive, but how they react when things go wrong mechanically. So first, let's look at the motivation. So we're currently witnessing a massive shift in transportation. Autonomous vehicles are entering real-world deployment right now, with major players like Waymo and Tesla leading the charge. The core driver of this success has been the advancement of deep neural networks models. These models are incredibly good at decision making in complex environments, which motivates everyone to integrate them into driving agents. However, an age-old question remains: are these agents safe? And more importantly, how do we measure that safety? To answer this, we must look at the distinction between the cause of an error and the outcome. We know that the component faults occur in real-world systems all the time, like a sensor glitches or a tire loses air, but not all component faults lead to a total system failure. The gap between a fault and a failure is where reliability engineering lives, and where the safety of these agents is truly tested. To bridge this gap, we need a way to test these agents safely. We can't just slash a tire on a real Tesla and on the highway to see what happens. This is why simulation environments combined with a fault injection framework is critical. It allows us to evaluate exactly how different driving agents respond to specific faults in control setting. Therefore, the objective of this project was to implement the fault injection framework for the popular Carla simulator to test DNN driving agents against faults and evaluate the latest agents on realistic faults that are overlooked due to limitations of simulator. So I mentioned Carla simulator, but what exactly is it? So Carla is an open source autonomous vehicle simulator. It provides a rich environment including more than 10 different town maps that simulate complex urban settings with objects, buildings, and traffic infrastructures. What makes Carla vital for us is how it handles the vehicle agent's perception. We can conveniently equip a suite of sensors that mimic real hardwares to vehicles in our simulation. For example, we can equip camera sensors, including RGB and wide-angle lenses. We can equip radar and LiDAR for depth and object detection. We also have accelerometer for physics sensing and GNSS for geolocation. We can see how these sensors pick up or fail to pick up the changes in vehicle dynamics by attacking the vehicle physics in this simulator. To test the autonomous driving agents, we utilize a framework called PCLA, or Pre-trained Carla Leaderboard Agents. PCLA allows us to access a library of 27 high-performing different autonomous driving agents directly with Carla. These aren't just random scripts, these are top-tier agents that have been benchmarked on the leaderboard. So there are three key reasons we chose the PCLA framework. The first reason is reproducibility. PCLA enforces a standard interface for sensors and controls. Instead of writing custom glue codes for every test, which can introduce hidden variables, PCLA ensures every agent sees the exact same data format. This guarantees that any difference in performance is due to the agent's logic, not the setup, ensuring the validity of our data. Secondly, it decouples us from the complexity of individual code bases. Normally, testing high-level agents like transfuser or interfuser requires building complex Docker containers or compiling specific ROS bridges. PCLA abstracts these dependencies away, meaning that we didn't have to manually compile or configure the environments for every single agent we want to test. Lastly, it allows for dynamic agent switching. Because PCLA wrapped these agents into a unified Python structure, swapping them is as simple as changing variables in our script. This was crucial for our comparative analysis, allowing us to immediately see how agent A reacts to fault, like flat tire versus agent B under identical runtime conditions. For the implementation strategy, our main goal was to observe how different AI driving agents respond to various faults under strictly controlled conditions. To do this, we developed our own fault injection framework that sits on top of Carla. However, one differentiator of our work is that, to the best of our knowledge, a lot of prior work in this field, especially studies that use Carla, focuses on sensor noise, digital glitches, like static camera feed. We hypothesize that Carla is designed to have high overall fidelity across many aspects of the simulation, including interactable entities, graphics, and physics. But the fidelity is not high enough, especially in hard to simulate areas such as physics. We sought to set ourselves apart by investigating physical and mechanical faults that are realistic and likely to occur in actual driving scenarios that may be overlooked by Carla practitioners that used it for projects with different focuses. We integrated the Carla PCLA framework mentioned earlier to enable that easy deployment of multiple agents. For this study, we selected a diverse set of autonomous driving agents to test. We wanted to see if the sensor architecture influenced the survival rates. Here represent the candidates. The first one we considered is Simlingo. This is a vision language action model that operates with a minimalist sensor setup of just one single camera. Combined with target waypoints, high-level language commands, and basic state data like velocity. It's particularly interesting because it tests if a model can rely on reasoning and language understanding rather than just raw sensor density. The second model we consider is Interfuser. It is a model heavily focused on sensor fusion. It steps up the hardware to 3 cameras, covering the front, left, and right, combined with a LiDAR unit. We included this to represent a robust, safety-oriented architecture that tries to build a complete world model before acting. Then we have Transfuser. This uses the exact same hardware as Interfuser, 3 cameras and LiDAR, but processes the data differently using the transformer-based architecture. This allows us to see if the algorithm matter more sometimes than the sensors when a fault occurs. Finally, there's Lav. This is the most sensor-heavy agent in our lineup. It's utilizing 4 cameras, including a specialized telephoto lens for long-range vision and LiDAR. Let's break down the faults we injected. Recall that our approach aims to bridge the physics gap by simulating messy correlated symptoms of real hardware failures. We chose these 3 specific faults to simulate them. Before we get into the realistic faults, we have camera blackout acting as the baseline faults. This is used as a reference point to compare the effects of other faults. At the highest intensity, this completely shuts down the camera, which allows us to see the performance of the model without one modality. We may also compare the robustness of this model against other realistic faults versus common blackout faults. Now we move on to the set of faults targeting realism. First, we chose tire pressure imbalance. We simulate an underinflated tire by reducing the friction of the front left wheel. This introduces a physical steering bias of about 8.6 degrees towards the flat tire. But to capture the realism, we also introduce a steering delay to mimic the sluggish response of a flat tire and slowing down the agent's ability to correct its course. Second, we have brake pad degradation. This simulates an aging braking system. We implemented a delay in braking response. Crucially, we also modeled the physics of brake fade due to heat buildup. Mathematically, this reduces brake power by a factor derived from that heat buildup, making the car much harder to stop the longer it drives. Third, traction control system loss. This simulates a partial loss of traction, specifically when the car is accelerating hard. We reduce wheel traction whenever the throttle exceeds a slip threshold of 0.4. This makes the car unstable during aggressive maneuvers. By injecting these specific physically grounded changes, we can measure if the AI detects the anomaly and corrects, or if it loses control. Now let's look at how we measure those failures. I will now pass on to Kyle for him to discuss how we measured them.
To understand the results of our simulations, we must understand how we quantify failures in our Carla simulations and what our key metrics mean. We define failure in 3 distinct ways. First, collisions. These are fatal failures detected through Carla's built-in collision sensor. When a collision occurs, we consider this a catastrophic failure and stop tracking recovery for that failure event. Second, we have lane deviations. These are recoverable failures where the vehicle strays more than 1 meter from the center of its lane. We measure this using Carla's lane deviation metric, checking periodically throughout the simulation. Third, speed violations occur when the vehicle exceeds the speed limit by more than 10 miles per hour. This indicates the agent has lost proper speed control. Now for our reliability metrics. Mean time to failure, or MTTF, is calculated by taking each failure's time from simulation start, summing them up, and dividing by the total number of failures. This gives us an average measure of how long the system operates before encountering a failure. A higher MTTF indicates a more reliable system. Mean time to repair, or MTTR, measures how quickly the system recovers from non-fatal failures. We calculate this by measuring the time from when a failure occurs until the system returns to stable operation. Recovery is defined as 3 consecutive stable measurements where the vehicle is back within acceptable lane boundaries, not violating speed limits, and maintaining relatively constant speed. It's important to note that MTTR only applies to recoverable failures. Collisions don't have a repair time since they're considered terminal events.
In order to carry out our fault injection experiments, we used the following approach. First, we started the Carla server using the helper script so that each experimental run can connect to a running instance of the Carla world. Then we can conduct all of our experimental runs. For consistency, each run is approximately 60 seconds, run at a fault severity level of 1.0, and carried out on the Town 10 HD map, where the vehicle is always spawned in at the predetermined spawn point number 2. In order to have a baseline to compare against when measuring the effects of the fault injection experiments, we ran one fault-free experiment per driving agent, which amounts to 3 runs total. For these runs, each driving agent was deployed into the world with 0 interference on our behalf. Next, we carried out the fault injection experiments. For each type of fault, we carried out 1 run per driving agent, which resulted in 12 runs, as there are 4 fault types, and each was carried out on 3 driving agents. Along with video footage, each run returns a JSON file which contains information such as the vehicle's XYZ coordinates, speed, lane position, and more at each tick, a tick being a single time step forward in the Carla simulation. One by one for each fault type, the results of each JSON returned by each driving agent were compiled into one JSON using a Python script, and using another Python script, the compounded JSON files were then used to create the visualizations of the results, which we will see in the next slides. These first results show a side-by-side comparison of the fault-free runs on the left versus the runs conducted where the camera blackout fault was injected into the vehicles on the right. Across all 3 driving agents, 14 failures occurred during the fault-free runs, while 523 failures occurred during the camera blackout runs. Broken down by driving agent, with blacked-out camera sensors, Interfuser suffered 198 more failures than its fault-free counterpart, SimLingo 98 more failures, and Transfuser 213 more failures. Notably, all agents during the camera blackout runs suffered from a fatal collision failure, while no agents during the fault-free runs suffered from a fatal collision failure. This may suggest that the dependability of the driving agents is highly dependent on the functionality of the vehicle's camera sensors. In terms of mean time to failure, SimLingo prevailed with the longest at 46.5 seconds, which is corroborated by the video demo we will see later. The next fault we injected was the tire imbalance fault, which introduced a steering bias in the direction of the underinflated tire, as well as reduced the friction of the underinflated tire. There were 25 total failures across the tire imbalance runs versus the 14 failures across the fault-free runs, a much smaller gap than what was observed for the camera blackout fault, but still more faults are observed in the fault injection run than the fault-free runs. Transfuser remained constant across the faulty and fault-free runs, with both resulting in 4 lane deviations. Interfuser saw 9 lane deviations during the faulty run versus only 4 lane deviations for the fault-free run, and SimLingo saw 3 speed violations and 9 lane deviations for the faulty run versus 6 speed violations for the fault-free run, a reduction in speed violations but an increase in lane deviations. Overall, the increase in lane deviations could be reflective of the effect of the steering bias introduced to mimic the effect of an underinflated tire. The mean time to failure results were similar to the previous slide, with SimLingo displaying the longest average mean time to failure. The average mean time to repair was 1.7 seconds. The next fault we injected was the brake pad degradation fault, which simulated the effect of worn down brake pads by introducing a delay in braking as well as a reduction in brake power. The total number of failures observed during the faulty runs was 18, 4 more than the 14 failures observed among the fault-free runs. Interestingly, although one might expect degraded brake pads to result in an increase in speed violations, the additional failures were due to lane violations and not speed violations, suggesting that perhaps the degraded brake pad fault did not have a large effect on the agent's ability to perform well overall. Transuser experienced 4 lane deviations for both the faulty and fault-free run. Interfuser experienced 4 more lane deviations during the faulty run than the fault-free run, and Simlingo saw 1 less speed violation and 1 more lane deviation. The average mean time to repair was a bit longer than the previous faults at about 2.9 seconds, and this is largely due to Simlingo's speed violations, for which the correction of returning under the speed threshold cannot be achieved as quickly as a correction for a lane deviation can be. The final fault we investigated was the degradation of the effectiveness of the traction control system. Across the faulty runs, 42 failures were observed compared to the 14 failures observed for the fault-free runs. Transfuser again remains constant across both runs with 4 lane deviations. Interfuser experienced 20 more lane deviations than in the faulty run during the fault-free run, and Simlingo experienced 1 less speed violation and 19 more lane deviations. The large increase in lane deviations, particularly for Simlingo, could be reflective of the effects of the loss of traction, as the fault simulates partial traction loss when the throttle is high, and Simlingo experienced several high-speed fault events. Additionally, Interfuser experienced 10 more lane deviations during the faulty run, which is a significantly large number and may suggest effect from the partial loss of traction control. The average mean time to repair here was about 1 second, which is consistent with the fact that less speed violations were observed. Now we're going to look at the demo part. The demo shows all of our runs one fault at a time. For each fault, the faulty runs will appear near the top of the screen, while the fault-free equivalent will appear below it. Some key insights from our results are first, that recovery does not equal reliability. A 100% recovery rate with a mean time to repair of under 2 seconds appears to be positive. However, the continuous failure and recovery cycles observed create unstable, unsafe behavior, which would not be able to meet real-world safety and reliability standards in this industry. Second, our findings imply that prevention can be more valuable than recovery, as even though our experiments exhibited a high recovery rate, they still largely demonstrated unsafe driving agency, which would not be suitable for real-world deployment. Thus, it may be more beneficial to prioritize fault tolerance in design over fault detection. Additionally, it's important to touch on the limitations of this work, as several environmental factors may have contributed to the robustness of our findings. Firstly, a key issue with our runs was the fact that objects like stoplights in the Carla simulation did not always consistently start at red or green across each run. Controlling the traffic lights is a non-trivial task in Carla, as traffic lights in Carla are part of the server-side simulation and are managed by the traffic light manager, for which traffic lights have internal states and timing cycles. A given traffic light may be at a different position in its cycle at the beginning of one run than at the beginning of another. And this is largely why we believe the results for Transfuser were unchanged across the fault-free and the faulty runs for all faults except the camera blackout, as Transfuser is stopped at a stoplight for a large portion of these runs. Additionally, Carla runs using Unreal Engine, which takes an immense amount of GPU computing power and RAM to be able to operate. Because of this, we were limited to running our experiments on the CS department GPU servers. An issue we consistently ran into was being kicked from the portal after a set amount of time, which limited us to 60-second runs for our experiments. 60 seconds is not a very long time for a run, and thus, this time limit potentially limited the robustness of our findings. A longer time allowance could have, for example, allowed Transfuser to get more runtime not stopped at a red light. Finally, this is the distribution of responsibilities among our team members. Tien handled the initial setup of Carla and the PCLA agents, as well as the creation of the injection and data collection pipeline. Kyle handled the creation of the data processing script to calculate the results from our simulations, as well as the creation of the visualization script to graph the results. And Kelly ran the experiments, created the demo video, and created the 3 realistic fault injection scripts.